My name is Remco. I work at Elastic at the Elastic Security Labs team, where I primarily focus on malware research, malware reverse engineering. I do have a slight preference for looking at Linux malware and Linux attack vectors. And I've been at Elastic for like 2 years now, I believe. Before that, I used to be in law enforcement. I used to be a security consultant, a pen tester. So I've had quite a lot of jobs. This talk today, a slight disclaimer, and in this day and age, we need to do that. This talk is not about Gen AI. It is not about machine learning. It is not about put in any buzzword, any hype, whatever. It is not about that. If you're disappointed by that, I'm very sorry. You can leave now. All jokes aside, no, the whole content is about vector search, and I know the two go hand in hand, but it's not about AI. What is it about? We are talking about 3 technologies: vector search, TLSH, or LSH more broadly, local sensitivity hashing, and disassembler output. Also, this talk is a little bit technical. I'll try to keep it within boundaries, but do forgive me for a little bit of source code and technical stuff in there. Now, what is more fun to start a talk that is not about AI by using an AI-generated image? Now, what do we have here? We have an image where you can see a little boy trying to get his ball off a roof using tools that are definitely not developed to use that for. I would normally prefer using a ladder instead of a chair. I would normally use anything except a rake to get that ball off, and I would definitely get a good spanking if you tried it to do this in this way. Sorry, all jokes aside. Let's talk about the technologies that you see here, and let's talk about the fundament. Vector search. A lot of people talk about vector search. A lot of people use vector search, even without knowing that they use vector search. And it's used in a lot of technology stacks. But does everyone actually realize what vector search is, how it's made, what it's doing below the surface? So, to get everyone up to speed, how does vector search or vector similarity search actually work? It'll start off by, we have some binary input. Text, bytes, images, whatever. We have some input that we want to find similarities to. In most cases, you would see that the data is being processed by a machine learning model, and then the output of that machine learning model will be a list of numbers. Now, I didn't have a lot of math in college, but apparently a list of numbers can also be called a vector. Who would have known? Now, what do? Or what does that machine learning model actually do? Let's say we have a machine learning model that we train to identify if an image is either cartoon or a real image. Now, the output of that model will normally not be it's a cartoon or it's realistic. No, it's a number, somewhere between -1 and +1. Now, that's overly simplified, but let's say we now want to identify if the image is also a mammal, or a bird. The output of this model would contain 2 numbers. One number for the cartoonishness and one for the mammalish. Now, bear with me. Now, we have the model trained, and the output will be 2 numbers. So we have a 2-dimensional vector that's outputted. And when we output, whatever we output, we can see that if you have a more cartoony elk, you will see a mammal, you will see that the images will be placed close to each other on the top. If you have a more realistic bird, you can see that there are multiple images close to each other, physically close to each other. And that is, and forgive me for anyone who actually worked on vector databases, this is really oversimplified, but imagine that you have a box, and everything that is similar to each other will be physically closer together within the database. And that is how you can actually find similar stuff in the database. Finding the stuff is the same way. You take an image, You process it by any vectorization process, in most cases a machine learning model, and you will output a list of numbers. Now in this case, this list of numbers will no longer be translated or stored in a database, but we will ask the database, hey, give me anything that is similar to this. Similar being a keyword here. So we put the query, we find the exact match, but we also find a list of stuff that is located near that database. And that is the whole purpose of a vector search database. Give me a list of stuff that is similar to this, as you can see in the result of the query. But most important of this part of the talk, remember, a vector is a list of numbers. We will get back to that very soon. But there is an example of a vector that you could use as a query. Next, a couple of quotes. And I removed the names, but there are very important people that are telling us the learning curve for vector search is very steep. Using vector search is very, very difficult. It is amazingly difficult to work with this technology. And I will say, the people who developed this technology, I've spoken to vector search developers, they're very intelligent. They're like top-notch engineers, and they definitely know what they're doing. But, come on. I will say, and this is my personal opinion, vector search, within Elasticsearch, but in most platforms that have been developed today, it's very easy to use. Let me be very clear. I'm talking about using that technology. How easy is it? That whole query that you need to do, come on, looks like this. Now, I know maybe not everyone in the audience is a developer or is used to using JSON, but this is the whole query. And what does this query say? I have a field that has a name. Here's my list of numbers, and give me the K, that's K nearest neighbors. Give me the top 5 candidates for this query. Well, it's basically as easy as saying select star from users where user ID is 1, right? It's really not that difficult. Now let's step aside from vector search for a second, and let's focus on local sensitivity hashing. Remember the image in the front? We're talking about 3 technologies. This one is the rake. We're getting that football off the roof eventually. Now local sensitivity hashing is a special kind of hashing. I'm using TLSH, which is the Trend Micro local sensitivity hash algorithm, developed by Trend Micro, of course. But more in general, local sensitivity hashing has some interesting properties. Normally, when you hash something, you would expect that if you change the input by even a single bit, the output will change significantly. The whole hash will be different. Now, the output of a TLSH is quite the opposite. What we see here is the output of 4 inputs where I calculated the TLSH, and I changed just a few bytes in the input every time. And I marked in red where the differences are. And yeah, it is quite difficult to see if you're all the way in the back, but I've marked in red where the differences are. You can see they're quite similar. Another property of using local sensitivity hashing is that you can calculate a difference. If I have 2 hashes, I can have the algorithm calculate, okay, how much was there changed between the 2 inputs. And this is a little bit arbitrary. There's not a lot of, you can't output like, okay, the input has changed for 80% or 50 bytes or any metric like that. But you can say there's a number that comes out, anywhere between 0, nothing has changed, all the way up to 300 something. And it depends on how big is the data that you're inputting, what type of changes did you make. But in most cases, you can say that anything where the output is below 80, you can say that the input is very, very, very similar, close to being the same. That is important. 80 is an important number to remember in this case. Now, look at these hashes. There are a bunch of numbers, but if we split them up, we know that the first number is of the output. That's the version that we're using. Then you have 3 hexadecimal numbers. That is a checksum, and then you have the actual hash, which again are hexadecimal numbers. Now let's say we translate those hexadecimal numbers back into a list of numbers. Looks familiar? We have a vector. Now, interestingly, one property of TLSH is the same as other hashes. You can't say, okay, let's sort all these hashes in alphabetical order and we now know which inputs are similar. You can't really predict where in the output of the hash algorithm you're going to see any change. So that is important because that would make any other technology redundant. You would only need to sort it. But it's a challenge to find similar files just based on looking at the hash without brute forcing. Just as an example, I know not everyone is a developer, but this should be easy enough to read. This is some Python code, and what am I doing? I'm putting data 1 and data 2, putting in exactly the same amount of bytes and exactly the same bytes. I'm calculating a TLSH hash over it, and I'm outputting both a TLSH hash and a SHA hash. Now, if you look at the output is exactly the same. Now, in the next example, come on. Finally. In the next example, we see basically the same code, but on the third line, you will see that I'm changing the first byte of data 2, and I'm upping that by 1. I'm outputting the same data again, and now you can see that there is actually a difference. Well, I confidently say you can see, no, I actually know where to look. If you look at the 5th character from the end in the second TLSH hash, you will see that there is a 0 flipped to a 1. The change is very, very small, but yeah, noticeable. So, but, if you look at the hashes, you see I just changed one single byte in the input, but the output hash has completely changed. So that is the big difference. Now, looking at the third tool, disassemblers. This is always fun. This is basically the screen what I look at all day, every and this is what I use to analyze malware. For anyone who hasn't used a disassembler, what you see here is a piece of malware pulled together and shown in its binary format, where in the big middle screen you see the assembly instructions that are being fed to the CPU while the program is running. And on the left you can see a list of functions that make up the program in its entirety. Now, how is this even relevant? These assemblers, you've got multiple, but this is my favorite. It's called Binary Ninja, and for anyone who ever used other disassemblers, there's a big one called Hexrace IDA. It's the de facto standard, and I'm trying not to use it specifically. But again, if you look closely at the disassembler output, what you see here is a part of a function, and whatever it is doing is totally not important. But what you will see is on the right, you have the instructions, the somewhat human-readable instructions that the CPU will be executing. But in the middle, you have the bytes. The bytes that are physically being sent to the CPU on in execution time. Now, these bytes are just big enough to feed to an algorithm, a hashing algorithm like SHA or TLSH. What does that allow me to do? I can take these bytes, I can calculate a local sensitivity hash over it, I can put that in a vector database, and I can then query the database for similar functions. As you can imagine, that function overview on the left, most of those functions, let me get back to this one, most of the functions that you actually see on the left aren't made by the developer. If you open a normal program, you will get 1,000 functions in there, while a normal malware developer maybe have written 100, maybe 50. Most of this code is being inputted by the compiler, by the operating system, by libraries, and it would really help my job if I can identify which of those functions are non-malicious, are not even being written by a malware developer. It's also very handy. It's also very handy if I can figure out if this function has been made by a malware developer, but it's maybe used in a different version of the malware. Now, let's take these bytes. We ran a project. We've calculated TLSH hashes over all the known functions and a sample set of data, and we started searching for similarities between them. one of the outputs was this one. A lot of gibberish, but on the right side you will see a table where a function was found to be in a sample. In this case, you can see black matter code and logbit code being in the same program. Now, we were doing a lot of experiments, and I thought, hey, this is interesting. Let's do a search. And it turns out that a week before that, our friends over at Sophos had figured out, hey, logbit and black matter are either joining hands or they're using each other's code. But it was actually proven that that there was code overlap between the two malware families. So we started digging in even further. And we found out, hey, we can see similarities between Klop and Ryuk malware. We can see similarities between Phobos and Logbit. And it's, of course, common. If you take ransomware samples, for example, there's only so many ways that you can actually encrypt the file. So there will be a limited amount of functions that you can actually use. But the overlap is significant. Going back to disassemblers, because it gets a little bit more interesting and why this tool is very important. Disassemblers have come a very, very long way since the first disassembler was developed. In the beginning, a disassembler would only show you like this middle part, where you could have the assembly instructions and assembly and the raw bytes. Nowadays, disassemblers are using a lot of techniques to try to get back from this machine code back to pseudo C code, so that a reverse engineer like me doesn't have to figure out all these bytes, but can just read normal code. Now, this code, they do that in different levels, and if I take Binary Ninja, for example, they will translate these bytes into an intermediate language, which is a little bit more readable. Why is that important? Let's take this example. I've written a little C program. It does absolutely nothing special, just you put in a string and it counts the number of A's in there, it'll reverse them and output some stuff. Now, what I then did is I compiled this program to be running on both a Windows system, using a Intel CPU, and on a Raspberry Pi using an ARM CPU on Linux. So we've got Windows and Linux, ARM and Intel next to each other, and if you then look at the output bytes, you see that they're not similar at all. Meaning that my whole idea of hashing these functions is completely going down the drain. I cannot identify functions that are being written for different operating systems. And with the upcoming of programming languages like Golang and Rust, cross-compiling for different platforms becomes way more easy. And malware developers are using their malware techniques that they developed for using on Windows, they're now using it on Linux, and the other way around. So, next step, if I look at the intermediate language that Binary Ninja produces of these two functions, you can see they're still different, but globally they're starting to look exactly the same. And that makes sense, because I've used the same programming language as input, I've written the same function, and I would expect that the output is at least similar. Now, what I did next is I put in this intermediate language, I calculated some TLSH hashes over it, and I saw that the difference is a factor of 60. Remember what I told you? 80 means that it's very, very similar. This is 60, means that it's very, 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 very similar. And now my problem was solved. I wrote a quick plugin, and in my disassembler, I now have this amazing output. To me, as a technician, this is very special. I open a function, and I can actually see, hey, I see this code before. I've seen it in black matter ransomware. And that makes my life way more easy. Now, there are more use cases to be thought of. Think about this. We have, of course, my life gets way more easy, and that makes it all worth it. But we can also have a pipeline where we get millions of samples going through the pipeline, and I can get an alert. Hey, black matter ransomware has an update. We only saw 2 functions that have changed. And these are the functions that a researcher needs to look at. That's very interesting. We can automatically create signatures for changed functions and updates. We can get a file, upload it into the pipeline, and get a report back. Hey, this file consists for 20% of emotet functions, 10% for Xordos functions, and we can start to track families even better. But this all comes with a price. And we had a company conference a couple of weeks ago where one of our directors was hammering on, do remember, you have to have an open mind, you can develop everything, but give yourself a few constraints. Let's talk about the constraints, because this technology isn't just out of the box for free. I took this from our own documentation, and this is the way that you calculate the amount of RAM that you need for using Vectorsearch. Consider this and consider the following big numbers. We process roughly 1 million unique malware samples a week, and that's not even a lot. That's on the low side. Our experiment showed that out of every function, we get about 200 unique functions that we actually want to store. And let's say we want to have a look back for a year. That means that we need to store 10,400 million vectors, or 10,400 million vectors in a Vectorsearch database. We'll do a slight calculation, and apparently we need 426 gigabytes worth of RAM to store that once. Storing it once, as we all know in IT, is a bad idea, because we want to do parallelism, we want to do search with multiple threads, and we don't want to have one system fall over and then have no copy of the data. So we'll need multiple copies. Now, I don't know about every company where any of you works, but I went to my director and said, I need a cluster with a few terabytes worth of RAM, and the answer was, no, we're not going to do that for your experiment. So now we're working on a pipeline to get that number down. This was basically an experiment that we did a couple of months ago, and now we're working on a project to make it more efficient, get all the duplicates out, and we're confident that we can get it even more efficient. We're also working together with the actual developers of the Vectorsearch part to make sure that we get the technology in that we need. And I'll get back to that in 1 second. There's also another technology constraint, which is the technologies that we use. TLSH, for example, it is a great library. It's a de facto standard for some pieces. But if you look at the code, it hasn't been touched in multiple years. Small lie, the original developer has touched it a couple of months ago, trying to improve some stuff. But yeah, although we're thankful for the code, it hasn't really been updated. And that means that there are some issues that have been being unresolved. Now, I have a very amazing, intelligent colleague, Christoph, I have to say, that took on the challenge of converting the code into C++. And he published his version with the disclaimer, and I made him promise that I would put this in. I can mention his fork, but I will definitely not say that the code is any good. He's working on it, but disclaimer, it's not good code. But it is in more than C++, so if you want to check it out, then please do so. Some closing remarks. Is this an actual good solution? No, definitely not. Why am I talking about it? Well, the thing is, Vectorsearch was made with the idea to support AI applications. But it's not the only use case that you can use it for. TLSH was developed to look at files, big chunks of data, not functions. There are different LSH algorithms available. The Ghidra now comes with bsim. We have, there are different algorithms, can't think of a few names now, but they might be more efficient. I haven't looked into them yet. But the message that I want to bring over is we now have these technologies that are readily available. TLSH is available, Vectorsearch is available, and especially with the attention that generative AI and other machine learning applications are now getting, development in the Vectorsearch space is going to be upped and upped even more. So we can expect more efficiency, lower costs, and available products. So if you have some technology, and it is made in a certain way, it doesn't mean that it's limited to that way. You can apply to different parts of the spectrum that you want to look at. Be creative. So again, yeah, it's not the most ideal solution, but it is working, and we're moving forward with it. I just got the 5-minute mark, so we've got 5 minutes ready for questions, if anyone has them.